This week, we're starting propositional logic, and logic is really the main form of math that we're going to be continuing with throughout the entire course. We're sort of done with set theory relations and functions until we see them in our syntactic semantic trees, but logic is something that will come up repeatedly and is going to drive our semantics. So last week, or the last 2 weeks, when we do set theory and we do relations, set theory covered things like nouns, adjectives. Relations are going to cover things like verbs and prepositions when we see them, or at least we put preposition with a copula is or copula be, and we make a relation out of that. Propositional logic is about the sentence or about the TP. We're not going to use TP, but we'll use an S instead, but it's about the sentence and it's about truth. So when you have a noun phrase like a dog or a proper name like Doug, that's not about truth, it's just about people. When you have verbs like John likes Mary, this is about pairs of people. There's a relation between John and Mary doing this thing called liking. But when you have an entire sentence, John likes Mary, we know that's either true or false, and propositional logic is going to let us track the truth of things and what happens when you take two sentences, say S1 and S2, and we put different conjunctions between them. And, or, if. What happens then? How does the truth change? And that's what propositional logic is about. So in this video, we're going to learn what it is and how to, create a formula that is appropriate or well formed. So propositional logic is used to model the truth of propositions. Now, a proposition, in our case, we can just think of it as a clause. So it has a subject and it has a predicate. Really, you can just count the number of predicates that you have, and predicate meaning verb phrases. And that tells you how many propositions are in a sentence. Now, one thing to remember is that a proposition is not necessarily just the words themselves. It's about the idea. So you can have the same idea expressed in two different very similar ways, and that's the same proposition. So we won't see any examples of that, but that's just a thing to keep in mind. A proposition is an idea that is represented by a clause. And propositions can be either true or false. So if you're in philosophy, you may use things like T's and F's, but we use ones and zeros. So when we see a zero, that means false. When we see a one, that means true. And if we have a formula that is well formed, we call it a well formed formula, and you can abbreviate it as WOOFs. So WOOFs, woof, 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 WOOFs. There you go. That's the IPA for that, WOOFs. So a proposition is just anything that can be true or false, so a declarative sentence. For example, I have two propositions here. My first proposition, which I'll call P, is turbulence is frightening. Okay? And I have a proposition Q, airplanes fly in the sky. So in each of these, we have the subject. So turbulence is the subject in the first sentence. Uh, Airplanes is the subject in the second sentence or second proposition. And then our predicates are is frightening in the first and fly in the sky in the second. So if we give each sentence a letter, P and Q, we can conjoin them together with the word and there's a special little symbol for this, which is called the caret. And you might notice it looks very similar to the intersection sign in set theory, and I represent set theory intersection with the word and it's the same way with this caret here. So this formula here, P caret Q, would be read as P and Q, and that would translate to turbulence is frightening and airplanes fly in the sky. So there's some conventions for which types of letters we use. With capital letters, that's when we have a specified proposition. So that's when you have a sentence. You would use a capital letter to represent that. When you just have arbitrary propositions, then we use lowercase letters, P, Q, R, S, and so on. So when we say arbitrary, this just means it doesn't have a sentence associated with it. It's just used for to demonstrate the structure or to demonstrate truth without having meaning. And that might not make sense right now, but we'll see how that can happen. When we have propositions in definitions and rules, then they're represented by Greek letters, so alpha, beta, gamma, delta, and so on. So whenever we see rules, we're going to see Greek letters. A lot of people use phi and psi. I've changed them to alpha, beta, and delta because I think, alpha and beta look like the letters they are, and they're not as symbol-y as something like phi and psi, which look very similar. So let's talk about the structure and what a well-formed formula is by referring to its syntax. And this is sort of like recursive generation, like we did in the first week of set theory, where I said we have an initial condition, we have some rules, and we can create giant structures. This is what we're doing here. So we're saying if you ever have any proposition or any statement on its own, let's call it alpha, that is well formed. So as long as you have alpha, it's well formed. You can take the negation. So this is not, this is the negation symbol. It's similar to our complement symbol. So you can take not, you can take any well-formed formula, and you can combine it with it. So we can have not alpha. If we have two well-formed formulas, let's say we have alpha and beta, there's four different things we can do with this. So if we have alpha and beta, we can join them together with the and symbol. So this is similar to the intersection. This is read and. We can take alpha, beta, I'll just write out the four different cases, and we can use or. So we can say alpha or beta, and you'll see this is very similar to the union symbol. It's called V. It's just like the caret is upside down, just like the intersection is upside down, so that means or. We have if alpha, then beta. So this is the arrow. This just means that if alpha is true, then beta is true. And the operator for this is sort of like the subset symbol in a way. Like if you have A subset B, that means everything in A is in B. If alpha arrow beta, that means if alpha is true, then beta is true. It's kind of a loose connection there, but it works really well with this last one. If you have two well-formed formulas, alpha and beta, you can do alpha left right arrow beta or alpha if and only if beta. In other words, alpha is the same thing as beta. And that could be represented by the equality sign. And if you remember, if you have A is a subset of B and B is a subset of A, then you have that A is equal to B. And it's the same idea with alpha left right arrow beta, or alpha if and only if beta. If we have alpha arrow beta and we have beta arrow alpha, then we have the two-sided arrow pointing back at them. So there's analogs to set theory here. So this is how we can build well-formed formulas, and we're going to see syntactic trees for these on the next page. But just with these, I want to check which ones are well-formed. So is Q not P well-formed? Well, okay, so P is an atomic statement or an atomic proposition. Atomic just means it's on its own. Q is one as well. So we have the negation attached to P, but because we have two things here, we have not P and we have Q, we need some sort of connective to join them together, but we don't have that here. So this is not a well-formed formula. It is not a WOOF. What about the second one? Well, we have Q, P, and R. So these are three different atomic statements. We joined Q and P together with and. We joined the unit Q and P together with R with the conditional, with the arrow. So yeah, that's a WOOF. It's well formed. It's taking two things, it's merging them together, except for the negation, which is just one thing. Well, there's no negation in B. In C, we have not, and then this whole thing. So that's fine, because if that's alpha, you can attach not to it. Inside, we have T arrow, not. I don't think I got the right number of knots here. It's really it's really irrelevant. It's a bunch of knots and then an S. So this is sort of like saying T is a subset of S with all these different complements. And that would be totally okay. So in this case, we have S, then not is being attached to that, not is being attached to that, and so on. So we can keep attaching individual knots to this. And then we have something over here, which we can call alpha, something over here, which we can call beta, and we're connecting it with the arrow. So yeah, this is also a well-formed formula. Only A was the one that was not well-formed. Now, if you didn't get it off just that, that's okay, because we can draw syntactic structures for these too. So here's all the different rules that we have, or different operators, to make a well-formed formula, and here's how they're made. So for example, if you have alpha on its own, you can attach a negation to it, and you can get not alpha. If we have two well-formed formulas, alpha and beta, we can attach a conjunction in the middle to get alpha and beta. If we have alpha and beta on their own, and we have an OR, we can bring them together to make alpha or beta. And we can do the same thing with the other one. So all these trees sort of look the same. So if alpha, then beta, and then we have alpha if and only if, so that's if with two F's, and there's beta there. So I want to give some examples here. Imagine we have something like P and Q. Okay, well we can attach a not to it to get not P and Q in brackets. If we have something, let's do an OR. Let's say we have P or Q on the left, we have Q and R on the right. We can attach an OR in there and bring them together to get P or Q, or Q and R. So these are how we can use our trees. So when we have alpha and we have beta, it doesn't just have to be a single thing. It can be a complex, well-formed formula there as well. Okay, so I want to draw the syntactic structure for one of these, and I already have it out here, but we can go through this step by step. So I want to draw not P or Q arrow, not S. So I'm actually going to do this side by side, even though I already have it, but if I draw it, I can go through it step by step, and you can also see what's coming ahead. So here, I'm identifying two things. I have this alpha over here, so not P or Q, this is a unit. And on the right, I have this not S unit, which I can say, okay, this is our second well-formed formula beta. And I see that I have a connective joining those. So I can split this up into three components. I can split this up into the connective. I can get my wolf alpha on the left, so this is going to be not P or Q. And on the right, I have not S. So that's my beta here. Now, if I take a look on not S on the right, let's do the right first. Well, this is a negation attached to an individual well-formed formula. So I can break this up into a not and an S. So the right side's done. Everything is down into its individual components. On the left side, I have not P or Q. So this right here is sort of like my alpha. It is a complex, well-formed formula, and I'm attaching a negation to it. So I can split this up into not and then P or Q. At this point, P or Q is a simple form. It has P, it has Q, it has a connective joining them. So I can split it up into three different branches, P, OR, and Q. So that's how we can draw a syntactic tree for a well-formed formula in propositional logic. Now, here's a more complex example, and if you can do it on your own, that's great. Pause the video, try it out, but I'm going to go through the solutions here. So I see a complex well-formed formula on the left. I can call this alpha. I see a complex well-formed formula on the right. I can call that beta. And I see a connective in the middle. So I can branch this off into three different branches with the connective in the middle. On the left, I have my complex formula, not P and Q arrow R. On the left, I have not S or not Q. Okay, let's do the left one first. So here I have not, and then I have this whole thing being negated. So I can say like, oh, that's our alpha here. So that means I can split this up into two components, not, and then whatever alpha is. So in this case, that's going to be P and Q, arrow R. Okay. On the right side, we have sort of the same thing. We have S or not Q, and that whole thing is being negated. So we can split that up as well into not, and then the remaining of alpha, which is S or not Q. Okay, let's take a look at P and Q arrow R. So we have this complex well-formed formula P and Q here. We have R on its own, so we can treat that as like beta, and we have a connective joining the two. So we can split this up into three components. We have R, we have the arrow, and then we have P and Q on the left. And with P and Q, we can now split this up into its three individual components, P and Q. Okay, on the right side, we have S or not Q. So S is like our alpha here, not Q is like our beta. It's being joined by the OR. So we can split this up into S or not Q. And at this point, all we have to do is break apart this not Q. So not Q is a combination of not and not Q, and then not Q is a combination of not and Q. So this would be the syntactic tree for this well-formed formula. And that is all we're doing in this video. If there's any questions, as always, ask on the discussion board, email me, and I'll be sure to respond as soon as I can.